All right, so if you're trying to land a job at one of the big tech companies, you've heard this a million times. DSA, data structures and algorithms. It's like the gatekeeper for interviews, right? It's the absolute bedrock of all software. So today, we're going to pull back the curtain and really figure out what these things are, and more importantly, why they are probably the single most important thing you're going to study. I mean, seriously, if you're in BTech, your seniors, your professors, everyone is telling you study DSA for placements. But why, right? Why are Google, Meta, Amazon, why are they so hung up on this one topic? It's a fair question, and that's exactly what we're going to get to the bottom of. Okay, so first things first, let's talk about why data structures even matter. Look, think about any app on your phone, Swiggy, Instagram, you name it. They're all dealing with just massive, massive amounts of data. And data structures, they're basically the blueprints for how you organize that chaos. So what is a data structure, really? Well, here's the simplest definition. It's a way to organize and store data efficiently. And I want you to burn that last word into your brain, efficiently. It's not just about storing stuff. That's easy. It's about doing it in a smart way. That one word, that's the whole game. So what do we even mean by efficiently? It really boils down to just two things. Number one, performance, which is all about time. How fast does your program run? And number two, memory, which is about space. How much computer memory does your code eat up? The holy grail, the perfect solution, is always the one that's fast and doesn't hog a ton of memory. And this right here is the billion-dollar reason why they care so much. Think about it. You scroll through Instagram, it feels free, right? But it's not. Meta is paying for every single little thing your phone makes the server do. They're paying for the electricity, the server racks, everything. So if you, as a developer, can write code that does the exact same thing, but say uses half the computer power, you've just saved them a ton of money. That's it. That's the secret. Okay, to really see this in action, let's start with the OG data structure, the one everyone learns on day one. Let's talk about arrays. So, what's an array? The easiest way to think about it is just a row of boxes. Simple. They're all lined up and each box has a number on it, which we call its index. It's just a way to keep a bunch of related things like a list of your friends' names all together in one place. Now, arrays have a superpower, and it's this. Getting something out of them is lightning fast. If you say, hey computer, give me what's in box number 5, it doesn't have to search. It knows exactly where box 5 is in memory, and it just jumps right to it. It's practically instant. This is a huge advantage. But every superpower has a weakness, right? Here's the catch with arrays. What happens if you don't know the box number? What if you're looking for a specific person, like Rohan, in your list? Well, the computer has no clue where Rohan is, so it has to do the dumbest thing possible. It goes to the first box. Is this Rohan? No. Next box. Is this Rohan? No. It has to go through every single box, one by one by one. You can imagine if you have thousands of names, this gets really, really slow, and that is the problem we need to fix. All right, so if the data structure, our array, gives us a problem, like this super slow searching, then an algorithm is how we solve it. Think of algorithms as the clever recipes, the secret techniques for making our data work for us. And really, that's the best way to think about it. An algorithm is just a recipe. It's a list of instructions. Step 1, do this. Step 2, do that. Just like a recipe for biryani tells you exactly how to combine rice and spices to get a final dish, an algorithm tells the computer exactly what steps to take to get the answer you want. Okay, so back to our problem of finding Rohan. We have two different recipes, two algorithms. The first is called linear search. That's the dumb one-by-one method we just talked about. But then there's binary search, and this one is genius. It has one requirement, though. Your list of names has to be sorted alphabetically. Now, think about searching for a name in an old-school phone book. You don't start at the first page, right? No, you flip open to the middle. If you're looking for Sharma and you land on Kumar, you instantly know that Sharma has to be in the second half. So you just throw away the entire first half of the book. Gone. Then you take the remaining half, jump to its middle, and do it again. You keep cutting the problem in half and half and half. It's so much smarter. Now let's put some numbers to this to see how insane the difference is. Imagine you have a sorted list of 10,000 names. If you use that dumb linear search, what's the worst case scenario? Well, the name you're looking for could be the very last one. So you'd have to make 10,000 checks. And what about our smart recipe binary search? On that exact same list of 10,000 names, guess how many checks it takes in the worst case? Just 14. Seriously, I'll say it again. 10,000 versus 14. Let that sink in for a second. And that right there, that is the power of picking the right algorithm. We're not talking about making something a little bit faster. This is a totally different universe of efficiency. This is the kind of thinking that saves a company millions of dollars in server costs. And this is why they want to hire people who can think this way. But look, arrays and searching, that's just the tip of the iceberg. This is just the beginning. As a developer, you get an entire toolkit of these things to play with. It's like having a toolbox full of specialized equipment. You've got stacks, which are perfect for something like a browser's back button. The last page you visited is the first one you go back to. You've got queues, which are just like a line for a movie ticket. First person in line is the first person served. Then there are linked lists, which are super flexible, like a chain you can easily add or remove links from. And you have things like trees, which are amazing for anything with a hierarchy, like a family tree or the folders on your computer. Every single one is designed to solve a different kind of problem really, really well. So let's bring it all back home. Look, anyone can learn to write code that works. It gets the job done. But the real challenge, the thing that separates an average programmer from a great one, is asking this one question about your own code. Okay, it works, but is it efficient? Because at the scale of a Google or a Meta, that's not just a technical question. That's the billion-dollar question.